Bonjour à toutes et à tous. C'est avec grand plaisir que je vous parlerai d'un livre que je suis en train d'écrire. This book is the fruit of a collaboration with two co-authors. My main collaborator, Professor Maya Sherbansky from the University of North Texas in the United States, and Dr. Sarah Munday from the University of John Cabot in Rome, Italy. The book is entitled Non-Invertible Dynamical Systems and is published by the Gruyter, 275-year-old publishing house. This is the first volume of a series of 3. In this volume, we introduce the reader to dynamical systems theory, to ergodic theory, and to thermodynamic formalism. Let me explain these terms. So first, what is a dynamical system? This is better explained through an example. Let's take a simple one. The function f of x is equal to 2x. So this is the function that takes any number and doubles it. It is sometimes called the doubling map. For instance, start with the number 1. Applying the function doubles that number, so 1 becomes 2. Applying the function again doubles the number 2, so 2 becomes 4. Applying the function again doubles the number 4 to 8. And then 16, 32, 64, 128, and so on. So upon iterating the function, that means applying the function again and again and again, the number 1 gets doubled each time, and the numbers grow to infinity. So we say that the trajectory or the orbit of the number 1 tends to infinity. The same behavior would be observed if we started from any positive number. So if you start with the negative number, then the numbers would double each time and they would tend to minus infinity. And finally, if you start with 0, well, doubling 0 still gives you a 0. And for this reason, 0 is called a fixed point. So it's a fixed point of this doubling map. The goal of dynamical system theory is to study the long-term behavior of these orbits, these trajectories. So in this simple example, the orbits of positive numbers tend to infinity. The orbits of negative numbers tend to minus infinity. And finally, 0 is a fixed point. And you can do that with any function. So try, for instance, the squaring function. F of x is equal to x squared. Then the numbers 0 and 1 are fixed points because 0 squared is 0. So 0 is fixed by the squaring function. Similarly, 1 squared is equal to 1. So 1 is also fixed by the squaring function. What happens to minus 1, for instance? Minus 1 squared is equal to 1. So that means that minus 1 is sent to 1. That means, in other words, that minus 1 is sent to the fixed point 1. And for this reason, minus 1 is called a prefixed point. What happens with numbers that are larger than 1? For example, 2. Well, 2 gets squared to give 4. 4 gets squared to give 16. Squaring 16 gives 256. And so on. So we see that the iterates of numbers larger than 1 tend to infinity. Something similar applies to numbers that are smaller than -1. So for instance, -2. -2 squared is 4. And then you see we're back to what happened with the number 4. So 4 gets squared to 16, then 256, and so on. So the negative numbers become positive. Negative numbers smaller than -1. They become positive numbers that are larger than 1, and then they follow the same trajectory as the numbers that are larger than 1. So they tend to infinity in this case. What happens with numbers that are between -1 and 1? For example, take 1/10, so 1/10. When squared, you get 1/100. If you square 1/100, you get 1/10,000. And then 1/10,000 squared is 1/100 million. So these numbers get closer and closer to 0. You take 1, you divide it by numbers that are bigger and bigger and bigger. So it gets closer and closer to 0. And therefore, the orbits of the numbers between -1 and 0 approach, between numbers -1 and 1, they approach 0. So for this reason, the number 0 is called an attractive fixed point. It attracts everything that is around 0, so between -1 and 1. And if you look at the number 1, then the number 1 is a fixed point, but this fixed point is actually repelling, because any numbers that are closer to 1, but not 1 exactly, they will go away from 1. So if they're smaller than 1, then they will tend to 0. And if they are larger than 1, then their orbits will tend to infinity. So all the numbers that are close to 1, but not exactly 1, their orbits go away from 1, and the number 1 is called a repelling fixed point. So that gives you an idea of what dynamical systems theory is about. This theory emerged in the late 19th century with some work due to the great French mathematician Henri Poincaré. And there are many different types of dynamical systems. Some involve real numbers, like the examples that I just gave you, and they are accordingly called real dynamical systems. Some involve complex numbers, and they are thus called complex dynamical systems. Some others consider symbols or letters from an alphabet, and they are hence called symbolic dynamical systems. Now, ergodic theory, briefly, ergodic theory is a branch of mathematics that studies dynamical systems, but from a statistical, also called stochastic, viewpoint. So in ergodic theory, we study the statistical properties of dynamical systems. By statistical properties, we mean properties that can be expressed through the long-term behavior of time averages versus space averages of various functions along the orbits of dynamical systems. Ergodic theory is based on measure theory, like probability theory, and its development was mainly motivated by problems from physics, from statistical physics more precisely. The first result is due to Poincaré, and it's called the Poincaré-Recurrence theorem. And essentially it says that under any finite invariant measure, almost all points in any subset of the space will eventually revisit that. Later in the 20th century, Georg David Birkhoff in the 1930s discovered another theorem, a major breakthrough in the theory, and this theorem is called Birkhoff's ergodic theorem. And this theorem says that under certain conditions, the time average of a function along most orbits is equal to the space average of that function. Many other results related to information theory have been obtained, and among others, the Shannon-Macmillan-Bryman theorem. Finally, thermodynamic formalism. Well, what is thermodynamic formalism? Well, it's a part of aggregate theory that concentrates on the study of notions like entropy and pressure of a system. So it's also concerned with the study of equilibrium states, where essentially the system finds a certain equilibrium through a variational principle. And it's also interested in the study of the concept of Gibbs states, Gibbs being one of the main physicists who developed statistical physics. And all of these notions appear in many natural contexts. Natural system theory and aggregate theory and their applications have grown incredibly over the last century, and they continue to grow today in the 21st century at a phenomenal pace. They are really a wonderful and fascinating world, and I invite you to learn more about them in your readings. Thank you very much for your attention.